So this is lesson 5, centripetal force and banked curves. And before we actually get into the notes, I just want to talk about a few different scenarios here. So the idea of having a banked curve is so that you can safely take a corner at a higher speed. So highways have banked curves. If you notice, they're not perfectly flat when you're going around a corner. So if you have a car that's driving on a level surface, all of the forces that are acting on the car are in the vertical direction. So you've got the weight of the car and the passenger, the Fg, or m times g, pointing down, and you've got the normal force that the road supplies. So there's no horizontal force generated here. So if there was no friction as this car was driving, there is no force available that could supply the centripetal force, which allows the car to make a turn or to move in a circular path. If you have the car on a banked turn, however, the normal force is no longer vertical. So the normal force is perpendicular to the surface of the road. So there actually is a vertical and a horizontal component to that normal force. So we'll have the y component and we'll have the x component. So now that there is a horizontal component to that force, and that horizontal component actually points towards the center of the circle, either along the radius, this component can be the centripetal force on the car. So the car, as long as it's moving at just the right speed, it will have a centripetal force available that could allow it to turn safely. So at the right speed, the car could safely go around a corner, even if it was covered in ice, which is somewhat counterintuitive. But the horizontal component of the normal force is right here. I drew it up there. Doesn't matter. It's pointing in the same direction. And that's the force that can supply the centripetal force to turn a car. All right. Now, for the notes. So highways have banked curves to allow cars to turn at higher speeds safely without requiring too much friction. So the car, even if it's a big car, it's a small car, it can round the curve safely. So let's draw a free body diagram. There is my car, it's traveling into the page. We've got Fg pointing downwards, and then we have the normal force that will be pointing perpendicular to the surface. Okay, so the y component of that normal force will be the force that's equal to the downwards force. Okay, make that a little better. So this is our normal force, and then of course we have Fnx and we have Fny. If we were to figure out equations for those components, well, x, this would be theta, and that would be theta, whatever the angle or the banking of the highway is. So if we're dealing with Fnx, that's the opposite side, so we're going to be using sine. So normal force in the x will be normal force multiplied by sine theta, whereas Fn in the y will be the normal force multiplied by cos theta. So in this scenario, our forces should balance out. So our net force in the y direction, so upper and downer forces, they should be equal. So F net in the y should be 0. And that's because the car is not lifting off the road, or going through or into the road, falling through the road. So up force has to equal down force. The up force is Fn in the y, which is equal to Fg. Now we can write a different expression for Fn and the y. Fn in the y is Fn times cos theta. And Fg, that's really just mg. So to actually have an equation that expresses what the normal force is, because so far anytime we've seen normal force it's been attached to either sine or cosine. So if we divide both sides by cos theta, we get that the normal force is equal to mass times gravity divided by cos theta. Now if we think about it, force of gravity points straight down, normal force does not. Normal force is actually the hypotenuse of this triangle. So if Fg and Fny are equal, normal force is actually going to be larger than the force of gravity because it's the hypotenuse of its triangle. Now, if we think about the x direction, so before on that other sheet, I'd mentioned that the normal force could provide the centripetal force. So centripetal force always points towards the center. So Fn in the x direction is what provides the centripetal force on the car. So Fnx provides the centripetal force. Okay, points to the center of the circle. I'm making this worse. There we go. So in the x direction, the net force is just whatever centripetal force is provided. Okay, so the centripetal force is really Fn in the x direction. Now, we have an equation for centripetal force. We know centripetal force is m times v squared over r. Fn in the x direction, if we go back over here, is Fn times sine theta. So we can make those two equations equal to each other. Centripetal force, which is mv squared over r, is equal to the normal force in the x, which is Fn times sine theta. Now when you have a bank curve like this, you want to know the speed at which you can navigate that turn safely. If you're above or below that speed, it's not going to be a perfect scenario. If your speed is too great, you'll need some friction to keep you on the road, so you would not be able to navigate the turn safely on an icy surface. But we are going to solve, we're going to get v by itself to figure out the speed at which you could navigate that turn safely with no friction. So Fn, lucky for us, all the way over here, we have an equation for Fn. Fn is really mg divided by cos theta. So we're going to take that and replace the normal force with it. So mv squared over r is equal to mg over cos theta times sine theta. Now because we have m on both sides, the m's can cancel each other out. So we're left with v squared over r is equal to g times sine theta over cos theta. Sine theta over cos theta, that's tan. V squared over r equals g times tan theta. And now we just have to get the r out of the denominator. So we multiply both sides by r. We're left with v squared is equal to r times g times tan theta. And of course, we want to get v by itself. So now we have v equals the square root of r times g times tan theta. Okay, so this here represents the speed at which the turn can safely be taken with no real friction. Okay, we can also rearrange this equation. Another useful form of it is if we have tan theta by itself, because sometimes you'll be asked what's the angle that the highway needs to be banked at to navigate the turn at this particular speed. So that turns into tan theta equals v squared over r times g. Okay, if you don't believe me, you can do it yourself. Move it from here to there. Or there's another way that I've seen this scenario looked at. Okay, our angle here, we won't necessarily know Fn. We'll know Fg most likely, so it's easier for us to find Fny and Fnx, but the opposite side and the adjacent side would mean we'd be using the tan ratio. So tan theta is opposite over adjacent. And in this case, our opposite side would be Fnx. And our adjacent side would be Fny. Now, Fn in the x direction, we said, was centripetal force. So let's write it as centripetal force instead. And Fny, well, Fny is really equal to Fg. Fg is really equal to mg. So we could say tan theta is equal to centripetal force divided by gravity force, which is just mg. Now, let's change this further. So this would be Fc is really m times v squared over r, still over mg. Now m divided by m, our m's go away. Tan theta is equal to v squared over r divided by g. Now when you're dividing by g, it's like multiplying by the inverse. Which gives us tan theta is equal to v squared over rg. Okay, these are exactly the same. Just two different ways of getting to the same conclusion. Okay, so this v represents the speed that you could safely take a turn with whatever radius banked at whatever angle. Whew. All right. Example, calculate the angle at which a frictionless curve must be banked if a car is to round it safely at a speed of 22 meters per second when the radius of the curve is 475 meters. Well, v is 22, radius is 475, g is 9.81. We're looking for the angle. Whoops, I'm losing it. Tan theta equals v squared over r times g. Tan theta is 22 meters per second squared. Don't forget to square it like I did. 475 meters. 9.81 meters per second squared. You get a bit of a decimal. Get my calculator. 22 squared divided by 475 times 9.81. That's our angle? No, we gotta take the inverse tangent. So inverse tan gives us 5.9 degrees. I'll just write that down. Okay, so that's a fairly shallow, not steep angle. 22 meters per second for context. It's about 80 kilometers an hour. So it doesn't need to be banked crazy high. All right. Let us look at another example. We have a car rounding a 515 meter frictionless curve in the highway. If the curve is banked at an angle of 12, what is the maximum speed of the car that it could safely be taken at? All right, this time let's use this version. 515, 9.81, tan of 12. Again, this is one of those cases where if you don't want to put units, not the end of the world. All right, 515 times 9.81 times tan of 12 gives us the square root of that number. If we actually square root it, 32.8 meters per second. And again, for a bit of context, that's 118 kilometers per hour. Okay? Now, a turn with a radius of 100 meters is being designed for a speed of 25 meters per second. Okay, so a 100-meter radius is not very large. Those of you who are familiar with track and field, think of what a 100-meter sprint is, and if that represents your radius, that's a pretty sharp curve. That's like very, very sharp. What angle should it be banked at so that you can do this safely? Well, 25 meters per second squared. Again, for context, 90 kilometers an hour. We want to be taking this very, very sharp circle. That's basically like a turn and come back. That's crazy. Anyways. We get 25 squared divided by 100 times 9.81. Okay, second function. 32.5 degrees. That is a very, very, very steeply banked corner. Not advisable. That'd be really hard to build. Anyways, this is the banked curves lesson. If you have questions, you know how to get a hold of me. Have a great day.